Hello, Mr. Kitchen, Goebelske, Richmondville High School Physics. Today we're going to pick up on page 7 of the review guide with electricity and magnetism. And we begin with electrostatics, which is the study of charges at rest, and the microstructure of matter, the idea that all matter is composed of protons, neutrons, and electrons. An object with an excess of electrons is negatively charged. To get an object positively charged, there is a shortage of electrons. And I think most of you know, like charges repel, unlike charges attract, but a lot of people don't know charged objects attract neutral objects, and they do that because the charges can redistribute themselves on the neutral object, and the charges that attract each other are always closer, and therefore the force is stronger than the charges that repel. To transfer charge, well, only electrons are free to move in solids, and they move from high to low concentration. Overall charge is conserved, but charge can be transferred from one object to another. It just cannot be created or destroyed. Coulomb's law, the Coulomb force or the electrostatic force acts between charged objects. The force is directly proportional to the product of the charges, and it's inversely proportional to the square of the distance between the center of the charges. So if the charges are half as far apart, you move them closer together, half as far apart, you'll get 4 times as much force. If the charges are 1/3 as far apart, there is 9 times as much force. Here's a representation of Coulomb's law. The electric force is K Q1 Q2 over R squared, where K is the electrostatic constant, and numerically it's equal to 8.99 E9 Newton meters per Coulomb, Newton meters squared per Coulomb squared. When we work with Coulomb's law, the force is the same on each object. Electric fields transmit the electrostatic or the Coulomb force. Electric field lines are the direction that a positive test charge would take if placed in the field, and they show us the strength and direction of the field. Where the field lines are close together, the field is strong. Where the field lines are far apart, the field is weak. But the field lines never cross. Field strength is the amount of force on a Coulomb of charge, and so our definition of the electric field strength is the electric force divided by the charge, and that's going to be in newtons per Coulomb. Sketching electric field distributions. I've got some sketched here on the left-hand margin. We start with a single point charge over here. I've picked a positive test charge to use. And if we put any little positive charges surrounding that, they're going to be repelled. So we have a radially symmetrical field that points away from that positive charge. If we have like charges, say 2 negative charges like this, the flux lines come toward each other and they repel. So they get pushed upward above the central axis here. They push downward below the central axis. Notice here in the center there isn't much in the way of field lines at all. There isn't much in the way of an electric field at that point. It's basically cancel out in here. And these arrows are pointing toward the negative objects because, again, they're the direction that positive charges would take. We have unlike charges down here where we have a positive on the left, a negative on the right, and the field lines going basically from left to right as they repel each other and bulge out a little bit. And then to finish this up, we have some parallel plates down here, and in the parallel plates the electric field lines are parallel to each other, and there should be a uniform spacing here because we have a constant field. The field between oppositely charged parallel plates is, as we just said, is uniform, and the field lines are parallel. And since the field is the same everywhere, the force on a charged particle is constant in this field. Potential difference or voltage. Work must be done to move charges parallel to electric field lines. Potential difference is the work done per Coulomb of charge, and so V, the potential difference, is W over Q, where V is the potential difference in volts. If we rearrange this equation, we get W equals V times Q, where W is the symbol for electrical energy. If Q is measured in coulombs, then W is measured in joules. But if Q is measured in elementary charges, then W is going to be measured in electron volts. An equivalent unit of energy. Current electricity is when we have charges in motion, and current is the rate at which charge flows in a circuit. I is equal to delta Q over T, and I is the symbol for the current. It's going to be measured in amps. An amp is just a coulomb per second, and the symbol for an ammeter is a circle with an A inside of it. These lines here are just connecting wires. Ammeters have very low resistance, and they're connected in series. And I have a sample that I've drawn here on the left. This happens to be just a simple series circuit, and I've got my ammeter, then my resistor, and then back to the battery. So the ammeter, all the electricity has to flow through the ammeter. The ammeter is in series with the resistance. Electron currents flow from negative to positive in this circuit, so the electron currents are going clockwise around this loop. Now, in order for us to have an electric current in this circuit, we need these things. We have to have a complete circuit. We need to have a source of potential difference or voltage, which is usually a battery. And a symbol for a battery is this. We make a short line, long line, short line, long line. The short line over here is the negative charge. The longer line over here is the positive charge or positive plate of the battery. Potential difference is measured with a voltmeter. The symbol for the voltmeter is a circle with a V inside of it. Once again, these are connecting wires, and voltmeters have very high internal resistance. If I were to hook up a voltmeter in the circuit, we do something like this. We put the voltmeter across what we're trying to measure, or we're going to hook up the voltmeter in parallel. And that's what we're going to write down at the top of the next page. Voltmeters are connected in parallel. Our example, well, it's not on the left, it's on the previous page, but we do have that example. In solids, electrons can easily move in good conductors. Metals are usually good conductors of electricity. Few electrons are free to move in insulators, and nonmetals are things that usually make good insulators. Resistance is the opposition to flow of electric current. Here's how Ohm's law is given to you in your reference table, R equals V over I, where R is the resistance measured in ohms, and this is the Greek letter omega, looks like a horseshoe, and it's the symbol for the ohm. Resistance is constant at constant temperature, but as temperature increases, the atoms and molecules vibrate more, and that makes the resistance increase. Wires themselves have some resistance, and we can calculate this. The resistance is directly proportional to L, which is the length of the wire. It's inversely proportional to A, the cross-sectional area of the wire. And it's directly proportional to rho, which is the resistivity of the wire. Good conductors have low resistivity, and resistivity is measured in ohm meters, ohms times meters. PRTs have a chart of resistivities. They're all given at 20 degrees C because as the temperature increases, it's actually the resistivity that increases. Here's a formula that's on your reference tables we can use to calculate the resistance of a wire, R equals rho L over A. And a resistor is a device that has a fixed amount of resistance. The symbol for it is this squiggly line here. A variable resistor is just a device where we can change the resistance. And we have a regular resistor over here, and then this part on the top is called the wiper. If the wiper is all the way over here, then the electrons will only go through a little bit of the resistor before they escape through the wiper. And conversely, if we move the wiper all the way down here, then the electrons have to go through most of the resistance before they can escape through the wiper. That's where we're going to stop this video, and we'll pick up on the next video with electric circuits.